Okay, I will start with the topic geometric deep learning. So this is the main highlight of the presentation. So up till now, what we have done was just building on the concepts, or you can say the background for this geometric deep learning. And there would be some mathematical equations also in this topic, but we'll not go into detail. Don't worry. We'll just give a highlight what this suggests, because this is the backbone of the graph neural networks that are being used in multiple application right now. And so if you go and read any research paper based on graph neural networks, so you need to have some idea or basic idea behind the equations or how actually the propagation take place. Once you get the basic idea, whenever you read the paper, research paper, you will get an idea what actually that suggests, right? So geometric deep learning. So why? So first thing is neural networks up till now that we have seen the convolution and all. So those basically work on Euclidean data. Now, what is Euclidean data? So those can be represented in n-dimensional space. You can say, for example, in this particular case, it is a three-dimensional coordinate system where this XYZ can be represented. So this Euclidean data would be a text, audio, images, or something like that. But what about non-Euclidean data? So any of you have an idea what is non-Euclidean data, or what type of data this geometric deep learning or this depends? One is fairly simple. We are already discussing it. Okay, anyone? Correct, Gaurav. Point cloud. That is one thing. No. Okay, so one is you can consider graph is one non-Euclidean data that we are discussing. The name itself suggests. So the graph can be represented in various ways. For example, this social network. So this social network is one big graph, you can say. Yes, Gaurav, correct. Message also. So this basically represents how one is connected with another group of people. So social network is one type of non-Euclidean space. Another is interaction network, like how one particular atom interacts with another, or you can say in the networking scenario, the network graph. The molecules. So molecules is also a non-Euclidean data space where basically how one atom interacts with the other atom based on the bond between them. So that is again a non-Euclidean data space. Functional networks is there. And a very good, or you can say relative to the geometric deep learning, or you can say CAD-CAM, is the mesh point cloud data. So why it is non-Euclidean, one thing. So for example, if you consider a mesh here, right? So if this is A and this is B, so if you want to find out the distance between these two, or you can say Euclidean distance, it would be basically this particular thing, right? But the same thing is not true actually in non-Euclidean space. So in non-Euclidean space, what would be the distance is calculating this thing and this. So we cannot fly in the air directly in the non-Euclidean space. So we basically traverse this triangle sides and then reach A. So the distance is slightly different compared to the Euclidean distance. And this is main thing that is why we cannot directly use the algorithms based on Euclidean data. We have to convert it somehow. Now, geometric deep learning is not one particular algorithm. So Michael Bronstein in 2017, I guess, just coined this term geometric deep learning in his literature review paper. So it is a review paper of multiple algorithms in present that are used for such types of non-Euclidean data. So the paper itself name is Going Beyond Euclidean Data. It's a very good paper. It just gives whole overview of the geometric deep learning that is currently out there. Types of layers it is, uh, types of architectures you can say. So all that is been summarized in this particular research paper. It's a very good one. And so this is not just a single algorithm. So it's a family of different architectures which comes under the umbrella of geometric deep learning. And it is not just based on the meshes. This is based on everything like on graphs, basically, social networks, molecules, and all this comes under this umbrella of geometric deep learning. So what is graph neural networks? So in simple terms, it is just we want to provide a graph and to some neural network, and it should provide me the output, classification output or segmentation output, whatever it is designed to. So it is just we want to make inference with the graph as an input data. That is the main idea of the graph neural network. Yeah, so machine learning problem with graph data. So what can be different types of machine learning problem that we can uh, use this graph neural network for. So, for example, there is a group of people, and those are somehow related based on, say, if they dance or not. So there are some characteristics, or you can say, which determines if this particular person is dancing or not, or likes to dance or not. So consider the green one as can dance and the yellow one as cannot dance. And we want to determine if the new person or this particular person that is there in question mark and it is unlabeled. So we don't know if he can dance or not. We want to predict if he is able to dance or not. So this is called as node level prediction. So here we don't know what the output of this means. You can say what this person based on the attributes that are there will he be able to dance or not. So this is called node level prediction. Another one is, for example, consider you are watching some OTT platform movies, you can say, I will not name any. So based on the previous movies that you have watched and what next you will watch, so they will just recommend you something, right? Like if you like more of action movies, then they will try to recommend some action movies to you and next time when you log in. So this is based on, so these are the nodes of movies that are there, right? And we have got some genres of the movies already defined, and based on those genres, will this movie be preferred to you or recommended to you or not? So this is basically called as link level prediction, or you can say edge level prediction. Now, these are the two separate predictions. Now, what about if you want to, so consider this as a structure of some molecule, some drug molecule, and you want to classify it as if this is a safe drug or a dangerous drug, which can be used for medicine or not, something like that. So for that, basically, we have called this as a graph level prediction, where entire graph is being classified as medicine or an harmful drug, something like that. So these are the three major problems where this graph neural networks attacks, or you can say, comes into picture. Now, what is the problem with graph data with CNN? So we have got a very good convolution neural network that works on images, and it's very good in works on different types of application, but it doesn't work on graph. And why is it? What is so different, or what is so problematic in graph that we cannot use it in existing CNN neural networks, basically? So first thing is size and shape. Okay, so anyone knows this particular guy? Anyone? Any friends? Okay, I guess no one. Okay, yeah, yeah, Ritvik, you are right. So it's Super Saiyan Goku 1. So this is a Dragon Ball Z character that I have shown here. So in CNN, we basically want to for example, we want to classify uh, if this character is Goku or not, right? So we have got a test data with multiple sets of images of this Goku, and we want to predict if it is Goku or some another thing. So for CNN, the one main thing that is there, that is the size of the input is same, or it should be same. For example, consider this as a 32 cross 32 image, then the other samples also should be of 32 cross 32, right? And even if it is not, the images can be easily resized. For example, if this image was around 48 cross 48, the lower image, but this can be downsampled to 32 cross 32 without losing much of the features, or you can say anything. So in general sense, the size of the input data is still the same for the image problem. But same thing is not true with the graph. So graph can be of variable length or variable size that cannot be fixed. For example, one graph can be of such 5 nodes, but the other can be of 6 nodes. So we cannot provide input with 6 node to a CNN which was trained for the 5 nodes as input. And the other thing is we cannot drop randomly any nodes from this input graph, because that node will have some features that are important, and we cannot drop it uh, so that, because this will also degrade the structure of the graph. Means the graph would be again a different thing then if you remove that particular node. So this is the main reason. Graphs should be of size independent thing, but for images or CNNs, we have to stick with one size. So this is the major problem that is there. Another thing is isomorphism. For example, just say, if I rotate, or you can say flip this particular image, right? So can you tell me that is this the same image or different image? Can anyone tell me?
Yes, it is the same image, but the
No,
mirror.
I can I differ. So images is just sets of pixel, you can say, right? So it is different that the features that are detected. So you know this particular guy, so you tell that it is the same image, but it is flipped. But once it is flipped, it is entirely a new image. The pixel values are changed. For example, this particular pixel here is a yellow, but at this point it is white or gray color, right? So it is entire new set of image, and it is not the same image anymore. But it is not true for graph. So graph are basically permutation invariant. So for example, if the same graph is flipped, but it is still the same graph. If you see the node connections and node connectivity, the ordering of the node, so the structure of the node ideally is the same. If you, even if you flip the graph, even if you flip it vertically, horizontally, rotate it somehow, but still it is the same molecule, or you can say same graph. So this is where another difference comes into picture, that graphs are permutation invariant. And this is the main reason why we cannot use the adjacency matrix, because in adjacency matrix, the ordering would be slightly different, and that you can say adjacency matrix for this both would be similar, and that is why we cannot differentiate between them. And that is the main reason why we cannot use this matrix directly into as an input to CNN. Even if we consider the size thing apart, adjacency matrix cannot be directly used as an input to CNN. So this is the second difference, or you can say second problem. The third is the grid structure. So images are well defined in the grid space. So the pixels are aligned and number of rows and number of columns are there. And based on that ij values, we are getting the signal of that pixel. But that is not true for the graph. Graphs are randomly spaced, and they do not follow proper grid structure as image have. And these are the three main problems why graphs cannot be used directly to CNN. We need to process it somehow or differently compared to image thing. But images can be considered as graph. That is again one thing. So if you consider these pixels, and those are the you can say structured set of graph. So something like this. So images can be considered as graph, but graphs cannot be considered as image. So that thing we need to keep in mind. So why it is hard to analyze graph? So these are the three main, you can say, criteria for CNNs basically. The locality, as we already know that CNNs can maintain the structure of the pixels nearby. So locality of the pixel nearby. So in CNNs, so these are basically difference between graph neural network and convolution neural network. In CNNs, we use something called as kernel or filter. As I mentioned, we use 3 by 3 filter and we slide along the image to get the features. So these filters are basically grids from beginning to end of the image and they are fixed, right? But in GNNs, the same, you can say, the locality of the graph can be defined by the locality of the neighboring nodes, you can say. So the neighboring node is the thing in graph neural networks, which is basically similar to kernel in convolution neural network. Now aggregation. So aggregation in convolution neural network is basically we apply the kernel, multiply the values of the kernel, and then sum the value to get the output signal, right? So that is the aggregation in the sense of CNNs. But in the sense of graph, uh, we basically understand how each node is affecting the input node, you can say, or the consider if this yellow node is there, then how this gray node and this particular yellow nodes are affecting that node. So the weights of those edges are also considered. So this is how aggregation take place. So it is in the neighborhood of this, while it is in the neighborhood of this. It is depending upon the kernel size, and here in the neighbor size. Now composition. So for composition, the CNNs are basically use functions of functions. Like we use layers stacked upon one another. So same thing in GNNs is that we are stacking the passing layers, or you can say message passing layers. So GNNs have got this term called message passing layers, and those are basically stacked one upon another. While here we basically stack a convolution layer, pooling layer, convolution layer, pooling layer, something like that. So these are the two differences and why it is hard to analyze graph directly using CNNs, right? Now we'll go to the main idea of GNN. So what actually it is. So
Hello.
consider this. Yeah.
Sorry for the interrupt, sir. Can you explain the message passing things again?
Yeah, so message passing we are just coming around what is message passing and all. But
Okay, okay.
for this thing, the message passing layer, so it is just a term called for graph neural networks, and messages are just signals, you can say. The signals are passed between individual nodes. So we are just coming to that particular slide in the next particular slide. And those signals are basically aggregated here. And here we are aggregating the pixel values with the kernel value. So that is the difference in CNN and GNN. Okay, so consider this graph, and we don't know if it is a node level prediction or uh, you can say link level prediction or graph level prediction. So consider this graph, and this graph has this particular node, and this node has some feature. We don't know which feature it is. For example, if you consider this as a person, each node is a person, then person might have different features like height, weight, age, male, female. So those are basically these particular features. Hello. Okay. Is anyone asking question or okay? So basically, these are hello. Okay, I guess no one is asking a question. So these are basically the node features that are there, and what we want to do is basically we pass it to a black box. Currently, GNN is a black box, and we want to embed this particular feature vector into some low dimensional, or you can say consider this feature has a size of something different size, and we want to embed in such a way that there is a similarity between these nodes which are there in the input compared to what is there in the embedding space. So for now, just stick to this is a GNN as a black box. And what this does is it outputs a graph with the layers, graph with a feature vector that is embedded in some space. And these values are different from what the input values are. And this values doesn't directly make sense. For example, what I can say, like it is an aggregation of its neighboring feature vectors as well. So we'll come to that part in the next slide. But consider this after passing through a GNN, we are having this as an output embedded feature vectors for each node. And we want to predict what this node is. Like if we are predicting if it's a male or a female based on some particular feature characters. So after this, we have got this embedded feature vector for this unknown node as well. And we want to predict if this is a male or a female, then we can do this as node level prediction. Right, we can compare this feature vector with this like feature vector for a male and a female already labeled data. And based on that, we can know if this is a male or a female. And this all thing is known as graph knowledge, this embeddings that we get. Now consider we don't want to do this node level prediction, but we want to entirely predict if this molecule is a medicinal molecule or a harmful drug. So based on these features, all the features are stacked together, and we compare those features with the already existing, or you can say labeled data, and see what amount or you can say what probability it is that it is a harmful molecule or it is a useful molecule. So that is basically a graph level prediction, this capital Y. And what exactly is in GNN is there are multiple message passing layers. Now, message passing layers are basically just uh, if you simplify it, it is just the aggregation of signals from the neighboring nodes and the features of the neighboring nodes and combining those features into some useful knowledge that can be used to separate this particular node from the other nodes. So these are message passing layers, but what exactly it is? So uh, in the lab session also, there is one exercise where we have already implemented it and how it is, how the features are aggregated. That also we'll have later on in the slides. So that will give some idea of what this message passing is basically. So it is just basically passing the uh, this feature information to this target node. You can say accumulating that feature information from the neighborhood features to the target node. So one main important thing in graph neural network is node embedding. Now just there are some equations, but I'll just go over briefly to that. So a node embedding is nothing but mapping a huge dimensional space to a smaller, or you can say lower dimensional space, but in such a way that the similarity in the input nodes is still maintained in the embedding space, so that the uh, for example, if you know this mapping, if you have worked with the surfaces, so surfaces, a three-dimensional surface point is mapped to a two-dimensional parametric space of a surface. So similarly, this is a node embedding where this particular embedded to a lower dimensional, consider lower dimensional space, such that there is a similarity between this ZU and ZV, same way as the original node U and V are similar. Now, this similarity can be in different, considered in different ways. We'll just go briefly after this. So our main goal is to map nodes so that the similarity in embedding space approximates the similarity in the network, right? Graphs are of variable lengths and all. So we basically want to lower down the dimension such a way that the entire graph structure would be represented similarly in the lower dimensional space as well. So our main aim is to have a similarity function where this is the embedding space value of U and V. And for simplification, the dot product of this, that is the, you can say cosine similarity. So the angle between these two vectors in embedding space is similar to the angle between those two nodes in the three-dimensional, or you can say original network space. So this is the similarity thing. And we have to define these three things. One is similarity, on what basis similarity is there. For this example, it is cosine similarity, and the encoding, or you can say the embedding, how this would be embedded in the space. So there are three steps basically for this. So first is we define an encoder. So that is the mapping from one space to another space. Same way as the 3D point in surface is mapped to a 2D parametric space point. So this V is the input of the graph and ZV is the embedding space value, or you can say embedding space node. Then we define the similarity function. So again, so this depends upon what properties you want to select for similarity. So for our case, we are considering that the angle between those two nodes, you can say, should be same in the uh, encoding or embedding space as well. So that is cosine similarity. There are different types of similarity, like Descartes similarity. So we'll not go into detail about that. So, but just consider we define some similarity function which approximates the similarity of U and V with this particular embedded space values ZU and ZV. And then we optimize it basically. So nothing, we calculate the loss and then we optimize this particular embedding space such that the loss is minimum. So this is the standard procedure for any optimization problem. So for simplicity, we'll go ahead with shallow embedding. So this is simply a lookup table. For example, if there is a table, so when a value v is there, we get z of v. And what is z? Z is just a table. So what you can consider here, I will just explain you. Okay. So consider we are embedding in two-dimensional space. So there is some n-dimensional space and we are embedding into two-dimensional space. So in that case, it would be just this thing. And the number of columns would be equal to number of nodes in the input graph. So that is one column per node. And this is, we are embedding in two-dimensional space. So there would be two rows basically. And this is just a lookup table. For example, if input is V, then V corresponds to V1, V2, something like that. So from the table, we'll take this V1, V2, and then we will proceed it. So it is just a simple example of how a shallow embedding is, or you can say a simple table where you map, if you have one value, you match its key value, and what is the associated value, will just fetch that value from the table. Nothing else, nothing in complex, just a simple table. So this is a shallow embedding. There are other methods like node to vec, deep walk. So these are advanced level method, and those are in actual practical use. They are implemented. So how to define a node similarity means on what basis you will define similarities. For example, are they connected or not? Are they sharing a neighbors or not? So those are the similarity parameters that we can define for our embedding space similarity. So it just compares sets of nodes based on the nodes they are connected to. So those are the similarity, right? As I already mentioned, there might be adjacency based, or you can say the cosine similarity, that is the angle, how similar they are in the true space versus the embedding space. There is multi-hop similarity, like how similar it is compared to its neighbor's neighbor. So that is based on the multi-hop similarity. So again, in that you can define to what depth you want to go. You want to go to just one uh, one neighbor or two neighbors, something like that. So this is Jacquard similarity index. So forget the equation, it is something related to similarity. And another thing is random walks. So random walks is mostly used nowadays, where we start from one node. Okay, I will go into this slide after this. So these are the parameters how a node similarity can be defined. Okay, so I'll just fast forward a little bit. So adjacency-based similarity, it is just, I will just fast forward a little bit. So there is a adjacency matrix, right, that we have formed, and this is the embedding space dot product that we have got. And so this is basically the weighted value in the adjacency matrix between U and I. For example, this is U node and this is V node. There might be some weight attached to it. So that weight is basically this. And in the embedding space, consider it came out to be something around 4. Just an example. So when you subtract it, it is 1 square. So that is just equal to 1. And we sum all these values for all the nodes, all the nodes. And we want to minimize this. Again, this is an optimization problem. So consider this value came out to be 10, but we want it equivalent to 0, or you can say we want to minimize this particular loss. So again, this is an optimization problem. We'll update some weights, and then again we calculate this particular values, and we came out to be say 2. So now again still we can approximate it to 0. So we'll again pass, or you can say optimize this particular parameters and reduce the loss basically. So this is adjacency-based similarity, where we use adjacency the two nodes U and V, and we want to find out similarity between U and V, right? So yeah, this is summing over all the pairs of the node, as I already mentioned. So other is multi-hop similarity. So it is k-hop neighbor overlap. So yeah, so consider we are at the red node here. So if you consider one hop neighborhood, then these green nodes that are there, we'll consider only those particular nodes for checking the similarity. If we are having two hop neighborhoods, then we'll consider up to these blue nodes, or you can say neighbor's neighbor will calculate the similarity for. And it is just the square of the adjacency matrix that are there, weight square, we'll consider. But it can be simplified again. So here, as you can see, instead of just a UV, we are having this k parameter. And this k is basically number of hops that you have defined. For example, for one hop or single hop, it is same as the adjacency matrix similarity. But for two hop, it would be a square UV. So the weights of between the nodes U and V would be squared off, and then we'll use it to minimize this loss function. Uh, so do let me know if you I got disconnected for some time while presenting, if I have any network issue on my end. Okay, so this can be simplified to something called SUV. And SUV is nothing but you can say Jacquard similarity or overlap similarity. So the formula I just mentioned in the previous slide, but don't go over to formula. We are just trying to find, so if there are two nodes, this is U and this is V. We want to find the overlap similarity between those two nodes. And that is what basically Jacquard index suggests. And again, we want to minimize the loss so that the embedding is as similar to what we have in the uh, original network, basically. So this is multi-hop similarity. Random walks is the most, you can say, used nowadays, and it is most generalized, I can say. So what we do is we take random walks from our U node and we find the probability how much time we reach the V node. So for example, in this particular image, this is U node and this is V node. So we'll have random walks multiple times. So for one time, I guess we reached with this V. So for other time, I guess I ran from this node to this node and this node to this node. So that is another thing to reach there. One time I reach like this way to V node. So similar type, we take random walks, and that random walk is an again hyperparameter, you can say. We take random walks from the U node, and we calculate the probability by what amount or how many times I have reached V node by just going randomly from one node to another. And that probability is what we basically embed it as a cosine angle, or you can say the uh, angle between those two vectors or nodes is the probability between this random walks. So have you got idea what I'm saying actually? So for example, if I took 5 random walks, and from 5 random walks, or you can say 4 random walks I took, and from 4 random walks, I was able to reach V for 2 times. Then it's basically you can say 0.5 times I was the probability is 0.5 to reach V if I start from U. And this probability is then considered as the angle between those two nodes, U and V, in the embedding space. So main advantage of random walks is as it is random, we can incorporate both local and high order neighborhood information. For example, in this particular case, we went to neighbor's neighbor and then we went to this, we reached V. In some case, we will able to get only in just one hop, we'll get to V. So we are able to aggregate the features of far away neighbors as well and nearby neighbor as well. And it's just purely based on random paths. Also, we don't need to consider paths for all the pairs. Basically, you can just define that I want to work on 5 random walks or 4 random walks. So whichever nodes are encountered in that particular random walks, only those features would be considered for embedding. So this would basically generalize the model well compared to walking on all the nodes, basically. So this is just the equation point of view, how this is been done. So for this probability, then we have converted it to a softmax thing, or you can say we can normalize the probability within the neighbor. So again, we'll consider the neighborhood set of NRU. So as I mentioned, we take random walks multiple times. So for one random walks, consider we from U to V, I went to Q2 and V. For another random walk, U, V1, V3, V2, and V, right? So for this, there are only, you can say one that is be required only one neighborhood to calculate. But for this there are 3 nodes that we have encountered. So we have to normalize this probability based on all the nodes that are there, right? And again, here there would be again a sum because we are taking random walks. So this would be for one random walk. So if I consider 4 random walks, then here again n is n0 to 4, or you can say 1 to 4. So we have to sum this 4 times on based on the random walks that we have encountered. And again, so this is optimization problem. So we have to minimize this loss so that the similarity in the embedding space is same as the similarity in the original network. So this is random walk embedding.